In model theory in the recent years. In model theory, there are stable theories and there are other theories. And stable theories are well understood already, and the other ones not so well. I mean, the subject is very topical. And they are important. For instance, first order theories are not stable. And new methods were suggested by Ludomir Newelski 20 years ago, and then developed by Krzysztof Krupiński in collaboration with Anand Pillai, Ludomir Newelski, and Tomasz Rzepecki. The leading figure in that, of course, being Krzysztof Krupiński. And these methods are related to topological dynamics. The talk will be about that. And nowadays, some top people in model theory are very interested in collaboration with Krzysztof Krupiński to pursue further work on the subject. In 2013, Krzysztof was awarded the prize of Polish Academy of Science, the same as Adam Osenkowski. I mean, the prize for significant achievements for people under 40. One of the most prestigious prizes for such people in Poland. Okay, Krzysztof, please, the floor is yours.
Thank you very much for the introduction and also for the invitation. It's a pleasure to be here at this conference back, because I was already at a similar conference 2 years ago. But 2 years ago, I gave a topic about some kind of like algebraic model theory, and this will be more about topological model theory. So originally, I was planning to discuss some nice and easy application, which is in the title, but I thought that on such conference where probably many people did not have any course in model theory or maybe even in logic, it's a good idea to spend some time and give a short course of model theory. So I slightly changed the sort of main point of the talk. So, okay, but let me start first from some purely topological dynamics part. So this is not like a comprehensive presentation. I will give some basic definitions and then try to see some of these notions within model theory. So, okay, so let us start from a situation where G is a topological, but mostly during this talk, it will be just discrete. And it is also a very important case in classical topological dynamics. So you can think just discrete group, you don't. And then a G flow. What is a G flow? It is a pair G together with X, where X is a compact, non-empty space, and G acts continuously on X. So if G is discrete, then G acts continuously just means that every element of G acts as a homeomorphism of X. That's it. And we say that Gx is a point transitive flow if X contains a dense G orbit. We have a topology on X. We have the notion of orbits, yes, under the action of G, and at least one of these orbits should be dense. And then a G ambit is actually a point transitive flow. But the point is that when we talk about G ambit, then we distinguish a point whose orbit is dense in X. Okay, so with this distinguished point, we call it a G ambit. And a very important notion, a G flow is minimal if it contains no proper subflows. Where, of course, we have a natural notion of a subflow. A subflow is a compact. It is a compact. Sorry, it is a closed subset of our space X, which is invariant under the action of G, and together with this restricted action, it becomes a flow by itself. Yes, so it's a minimal flow. And it is not true that every flow is a union of minimal flows, but still minimal flows are the most important subject of study in topology, at least in abstract topological dynamics. So, and now we have a basic fact which follows from Zorn's lemma that each flow contains the minimal subflow. You just take a chain, so linearly ordered collection of, with respect to inclusion of subflows, and then you take the intersection of this chain and you get a minimal bound. So by Zorn's lemma, you get a minimal element in this order of subflows, so which is just a minimal subflow. And let us look at one of the most important examples, classical examples. This is Bernoulli shift. So G is the group of integer acting on the space 2 to the z, where on 2 means 0, 1, two element set 0, 1, and 2 to the z is the product just with the Tikhonov product topology. So you can also think about 2 to the z that these are infinite sequences, but indexed not by natural numbers, but by all integers. So they are like infinite on both sides. And then we have the obvious action of the group Z on this space 2 to the Z, which is just shift. So formally, an element K acts on function F by this formula. When you compute it at the argument N, you get F of N minus K. And now to see some of the above notions. So, okay, so this is a flow. It's easy to see that this action is by homeomorphisms, which follows immediately from the definition of the product topology. And now if you take an element F0 in X, so you can think like sequence indexed by Z. And if this F0 contains all finite 0, 1 sequences as subsequences of consecutive elements, so yeah, you take any finite sequence and I'm assuming that inside F0 it appears as a sequence of consecutive elements somewhere in this infinite sequence. Then by the definition of the product topology, one easily sees that the orbit of F0 under G is dense. Okay, it is dense because every finite subsequence, every finite sequence appears somewhere in this long sequence. So it is dense. So this means that this flow, this Bernoulli shift, so group G acting on X, it is a point transitive flow. And for example, I can distinguish any F0 like that, and I get an ambit. And then if F is a periodic function, like from high school, periodic function, yes, so there is N such that for every X, F of X plus N is equal to F of X, then the orbit is of course finite. Yes, because I can get different elements only going to N. When I go farther, then I repeat the same elements. So it is finite, so also closed. Every finite subset of our compact space is closed. So this means that the flow G times F, the orbit of F is minimal. Because the group G, it is a subflow because it is flow, because it is closed and it is an orbit, but it does not have any proper subflows because it's transitive, because this is an orbit. Okay, so it's minimal. So so we have an example of a minimal subflow, which is like quite trivial in this situation because it is finite. But there are also other minimal subflows of Gx not coming from periodic functions, which are infinite. And this I leave as a non-trivial exercise to construct such guys. Such something called Morse sequences is involved into it, but there are also geometric constructions. But it's not so trivial. It's not like for 1 minute exercise. But there are. So there are finite minimal subflows and infinite in this example. Something happened. Okay. So here is our picture. And now we have the following general fact that for every fixed group G, there is a unique up to isomorphism universal G ambit, where universal means that when you have any other G ambit, so this space X with the action of G and distinguished point with dense orbit, then there is a map between, there is a homomorphism between flows from this universal one to the other one, which means which means a continuous map between spaces, which is G equivariant, so preserving the action of G and mapping the distinguished points. So there is such a guy, the universal one. It is unique up to isomorphism of flows. The existence is easy to show by some general reasons, but here there is actually a concrete description, more or less. This is namely the check-stone compactification of the group G. So the space of all ultra filters of subsets of the group G, and the distinguished point is the principal ultra filter at the neutral element of the group. So the ultra filter consisting of all sets containing the element E, the neutral element of the group. And universality follows from the universal property of the check-stone compactification. It's a fundamental result about check-stone compactification. But we also have a theorem about minimal flows. For every group G, the same, there is a unique up to isomorphism universal minimal G flow. And here the existence is pretty easy. You can take the set of all minimal G flow. Let's say we can choose representatives up to isomorphism, and then they form a set. And then you take the product of all flows in this, of all minimal flows, of all these representatives. You take a point in this product, you take the orbit of this point, and you take the closure of this orbit. And by the choice that you took all the minimal flows, you easily get that it's universal. But it does not give you a concrete description. It's like an abstract proof. Universality is not so trivial. It's a theorem, not that difficult, but also not trivial. And some of the, I don't know, it's very sensitive, this. Okay, so some general goals of abstract topological dynamics. I am not talking about like considerations just like in differential equations where we focus on some very particular properties of some concrete flows, but abstract topological dynamics. So this is a study of flows, and one of the fundamental goals from the very beginning of the subject was to classify minimal G flows. And here there is a very deep structural theory with lots of tools and special classes of flows. So there are flows like equicontinuous flows, distal flows, whatever it means. And there are theorems, deep, difficult theorems, which describe the structure of an arbitrary minimal G flow in the sense that it is in some sense built from flows which are very nice, like equicontinuous flows and so on. And people like Furstenberg, Glasner, Ellis, Auslander were involved with the most fundamental work by Furstenberg here, I think. And another topic is to describe the universal minimal G flow for a given group G. And it's usually a big enterprise to give some understandable description of this object, which we know that exists by the previous fact. But the point is how to identify it. And here, Kechris, Pestov, Todorcevich developed a beautiful theory where in the case of, at least for the groups G, which are the groups of automorphisms of certain structures in the sense of model theory, they were able to prove general theorems which give description of minimal flows, of universal minimal flows. Okay. And in the mid, as Eva mentioned, in the mid-2000s, Neversky came up with an idea of applying topological dynamics framework to model theory. And the point, as I mentioned, I would say the main object in topological dynamics is a flow, is the notion of a flow. And the point was that in model theory, on the other hand, in model theory, one of the main tools and main objects to study are spaces of types, which I will define later. And the main idea here was to see that the very general idea that type spaces can be naturally treated as flows. So in this way, topological dynamics come into the picture in model theory. And the idea was, first of all, that some fundamental results of the so-called stable group theory, so group theory for groups which are definable in stable theories, so various theorems there are, in fact, can be seen as topological dynamical statements. And so there was a hope that one can prove more general results using some other topological dynamics tools which are not available just you know, if you don't use them, then you don't have such tools in stable groups. And my personal look at the subject is that various type spaces are naturally flows, and topological dynamics yields new notions and methods to study various important objects in model theory. These are the so-called strong types. So this is with my contributions here, definable sets also, and other model theoretic objects, and prove new results about them. And on the other hand, model theory gives new descriptions of various objects already existing in topological dynamics. It also yields new objects which were not studied in topological dynamics before, and may lead to new results or new proofs. And there are already such situations. So, for example, if somebody is familiar, there is a notion of a Born compactification of the group, and there are general constructions. So in model theory, we have something like almost trivial from the point of view of model theory description of the Born compactification of the group. So this is a classical notion, but there are many others. And for example, there are some applications of model theory to topological dynamics, which I will maybe briefly mention here. So these two slides may be a bit vague, okay, because the various notions are not defined, but I just wanted to show sort of a variety of considerations on the border of topological dynamics and model theory, just so that you see that it's not just one application, but the whole areas. So sorry that it will not be very precise, but then I will pass to more concrete things, definitions, and so on, to discuss some basic stuff. So the first point is, for example, this theory developed by Neversky, where he identified some flows in model theory. He proved some results about generating groups in finitely many steps in the case where a group is covered by countably many sets satisfying some assumptions. So it is generated by finitely many of them in finitely many steps. And this actually is this easy application that I am going to discuss today in the second hour. And Neversky also studied the so-called Ellis group, which is a notion in topological dynamics, and compare it. He found an epimorphism from this Ellis group to the something that we call definable Born compactification of the group. And his conjecture was that, so these are some invariants. One comes from the topological dynamics, and this definable Born compactification comes from model theory. And there is an epimorphism. And Neversky's conjecture predicted that it's an isomorphism. And it is very influential. So many people studied this, and they gave a counterexample to Neversky's conjecture. Then by my work and my work with Gismatulin, one can obtain that it's completely false. I mean, there are lots of counterexamples, but under some nice assumptions, which is the next dot, which is definable amenability, Chernikov and Simon proved Neversky's conjecture, which is really a beautiful result and a beautiful proof. So then definably amenable groups and theories. So this is another aspect of topological dynamics in model theory. So probably some of you know, an amenable discrete group, it's a group on such that you have a measure on the Boolean algebra of all subsets of this group. You have a measure which is finitely additive, probability measure, invariant under the action of G. So when I talk about definably amenable, I mean there is such a measure, but not on the algebra of all subsets of the group, but only of definable subsets. I will define what it means definable, but this is the main point in model theory. We don't look at abstract all subsets, but only those which can be defined using the language in which we are working in a given structure. Okay, so it's a weaker notion than amenability, because the measure is required to exist only on some subalgebra. And together with Hruszowski and Pillai, I defined an analog of this notion, not for definable groups, but for first order theories in general. And there is a beautiful theory developed by many people of this amenability issues in model theory. But amenable theories is my work with Hruszowski and Pillai. So, and this dot, I think it contains the deepest applications so far of model theory, of topological dynamics in model theory. So this was done by Pillai, Rzepecki, and myself. And there are several papers. Some of them are Pillai and myself, and some of them myself and Rzepecki, and one of the fundamental is also the three of us. So here the point is that you know that there are some objects associated to any first order theory. For example, there is a notion of a Galois group of a theory, which generalizes the absolute Galois group of the field of rational numbers. But this abstract group in general, it does not have to be Hausdorff. There is a certain logic topology there, but it does not have to be Hausdorff. And there was a question how to treat it as a mathematical object. And our discovery was that using the Ellis group coming from topological dynamics, or rather its canonical Hausdorff quotient, we can explain better, understand better mathematically these Galois groups of first order theories. Namely, we presented them as quotients of compact groups by, for example, dense subgroups. And this allowed us to prove some maybe surprising result using, so descriptive set theory also come to the picture there. And so it's like descriptive set theory, topological dynamics, and model theory. And using this topological dynamics in model theory, we were able to prove that model theoretic simplicity of the Galois group, so which we say there's some kind of type definability, it is equivalent to descriptive set theoretic simplicity, which is called smoothness. So this is using this topological dynamics. And recently, Krzysztof did something quite amazing, namely, he developed a counterpart. We adopted something from topological dynamics to model theory, and he defined a like more model theoretic counterpart of our object, and then he very recently used it in another paper to prove some results about approximate subgroups, which is a very topical thing in additive or multiplicative combinatorics, for example, by Tao and various other people. So, but it's a very hard paper by Krzysztof. It's like 100 pages, quite difficult to read. Yeah, there are two papers actually. But anyway, he undertook these considerations, or was motivated by these considerations that we did before. And then there is Krupiński-Todorczewicz theory. It's not very model theoretic, but it at least uses model theory context, namely it uses automorphism groups of first order structures, so of models in the sense of model theory. And here they were studying the so-called Frezet structures, and it's a beautiful idea again that they found a dictionary between some combinatorial properties of these Frezet structures and the dynamical properties of the automorphisms groups of these Frezet structures. So for example, the so-called Ramsey structural Ramsey property, roughly speaking, is equivalent, for example, to extreme amenability of the automorphism group, which means that every action on a compact space of this automorphism group has a fixed point. So this is really something nice. And together with my two postdocs, Slavko Moconia and Jungkook Lee, we developed a model theoretic counterpart of this. So which leads to, which on the one hand, it contains like analogs of results proved by Kechris, Pestov, Todorczewicz, but it also contains completely new results, for example, related to the property of profiniteness or finiteness of the Ellis group. So this is something nice. And there are a few other things that maybe I will not discuss so I mean, very briefly, let's say. So there are, in model theory, as Eva mentioned, there is a class of stable theories, which is like the core of model theory. There are deep structural results there. There are also other wider classes theories like NIP and some others. And model theories developed those classes of theories motivated by model theory. And on the other hand, people in topological dynamics, they were developing their notions motivated by, I don't know, by describing the structure of minimal flows and so on. And it is quite amazing that people discovered, like Beniakov, Ibarlucia, and others, that these discoveries are very similar. So if you interpret it in a correct way, then stability in the sense of model theories is the same as weak almost periodicity in topological dynamics. And NIP in model theory is the same as the notion of a tame system. So So it shows somehow that these notions are not accidental. In different areas, people somehow discover the same notions, although expressed in a different way. And there are also applications of model theory to algebras of functions and compactifications of groups and some other stuff. Maybe I skip it. And then I just wanted to mention a few more definitions. So in particular, topological dynamics gives us various notions of large sets. And this is one of the ideas that topological dynamics may work outside of this nice stable context. So first of all, we have a generic, or in topological dynamics, people say synthetic, but in model theory, generic subset of a flow is just a subset U whose finitely many, let's say, left translates covers the whole space. So generic means that finitely many translates of this set covers the whole space. So it's big in this sense because finitely many. And then weak generic means that you can find a non-generic set such that if you take the union, then you get a generic set. So U does not have to be generic, but if you add something non-generic to it, you will get something generic. Okay, so this was defined by Neversky, but actually in topological dynamics, they also considered this under the name of piecewise synthetic set. So, and a point, this was about subsets, but now a point of the space of the flow is generic or weak generic if every neighborhood U of P is generic or weak generic in the sense of the above definitions. So a point is generic if every neighborhood is generic, meaning finitely many translates of this neighborhood covers everything, and P is almost periodic if it belongs to a minimal subflow. So points which are in minimal subflows are called almost periodic. And now by gen of X, we denote all generic points of X, by W gen all weakly generic, and by A pair we called all almost periodic points. And Neversky observed the following easy thing, that weakly generic points, they form, this is exactly the closure of almost periodic points. And as I said at the beginning, there is always at least one minimal subflow, which is non-empty by definition. So it means that there is always at least one almost periodic point. Okay, because almost periodic points are in subflow. So it means this A pair is non-empty. So its closure is also non-empty. So there is always at least one weakly generic point. And this is an advantage in comparison to generic. So for example, in stable group theories, there were always the so-called generic types, and they played a key role. But outside stable context, it may happen that generic types does not exist, but weakly generic type always exists. So this is an example of this, what I mentioned before. So the second part, if generic is non-empty, then generic, weakly generic, almost periodic is the same, and this is a unique minimal subflow of X. So then there is a unique minimal subflow in general node. So whenever there is no uniqueness, like in this Bernoulli shift, there is no uniqueness. I said that there are finite minimal flows and infinite. Then immediately we get that there are no generic points. And here actually I wrote something about this. So in this Bernoulli shift, if you take F0 with dense orbits, so I mentioned at the first slide that there are such points, then this is not an almost periodic point, because we know that the whole flow is not minimal because it has this proper finite, for example, minimal subflows. So this point is not almost periodic. But on the other hand, periodic points are dense in 2 to the z, periodic functions. By the definition of the product topology, it's easy to see. So by the previous observation of Neversky, we get that weakly generic points, they form the closure of almost periodic points. But periodic points are in particular almost periodic, which I explained in the first slide. They generate minimal subflows. So we have this inclusion, but I said in the previous line that periodic points form a dense subset. So it means that the closure is everything. It's 2 to the z, because periodic points are dense. It's 2 to the z. So it means, so this implies that weakly generic points is just 2 to the z. So every point here is weakly generic, but on the other hand, as I said, generic points, they form an empty set. There are no generic points. And maybe one concrete example, another concrete example. If you take Z acting on the unit circle, just in this way that NZ is alpha to the n times Z, where alpha is an element of the circle which is not a root of unity of any degree. So it's easy to see that such powers alpha to the n on the unit circle, they form a dense subset, actually a dense subgroup. This flow is minimal because it doesn't matter from which Z you start. If you take the orbit by the denseness of alpha of the set of all alpha to the n, you get that the orbit is dense. So it means that every orbit is dense, so its closure is everything. So the flow is minimal. There are no and actually you can easily see this is actually always true in a minimal flow, that the generic points is everything, is the whole space. So and I will skip the proof because I more or less mentioned this. So here we have an example where there are no generic points, and here we have an example where generic points is everything. So we see that various possibilities come to the picture. And now I would like to give, okay, this was the place where I changed the original plan, and I'm going to spend a few slides giving a short course of model theory. Okay, so you can focus now. And but if you like miss some definitions or something, then don't worry, because later when I will be showing this nice and easy application of topological dynamics and model theory, I will use only a few of these notions, like the notion of a type and saturated model. So don't worry if you forget some of the definitions here. So, okay, so the basic, the starting point to do model theory is fixing a language or signature, which formally consists of function symbols, Fi, relational symbols, Pj, and constant symbols or just constant Ck. And for example, if you want to talk about group theory, you can consider the following language consisting of one binary symbol, which is then interpreted as just group operation or group law. And for example, the one constant symbol, which will be interpreted as the neutral element of the group. But you can also use just the dot, and then you can somehow, by axioms, you can say that E exists. And you can also consider the version where you add the one unary function for the taking the inversion, the inverse element. But okay, this is, let's say this we will take as the language of group theory. And now using symbols of L of the language, so these from the first line, logical symbol of equality, variables, logical connectives. By this I mean, let's say conjunction, disjunction, and negation. Yes, and quantifiers, they're existent for all. You can build recursively the collection of all formulas in the language L. Intuitively, it should be clear how to do it. I'm not going to write a formal definition. For example, the following formula is a formula in the language of group theory. So here we have this dot. So I can write such a formula. There exists Y such that negation of X times Y is equal to Y times X. This is a correctly written formula in the language of group theory. I'm not saying about the meaning of this formula. I am just saying syntactically, this is an example of a correct formula. And then what is an L theory? Or a theory in the language L? It is just a collection of all L sentences. So this means L formulas without free variables. So I didn't say free variable is a variable which is not under the scope of any quantifier. So in this case, this is X in this example. Okay, so all L sentences, so without free formulas, without free variables. And then what is an L structure? So a structure in the language L. So this is just a set M. And here, to avoid some false statement, I will be assuming that structures are non-empty, okay? Because otherwise I would have to add some assumptions in some places that the structure is non-empty. So assume non-empty. So it's a set together with interpretations of all symbols of the language. For example, if Fi is a binary function symbol, so binary means with two variables. So like for example, this dot in the language of group theory, then it should be interpreted somehow in M. And by interpretation, we mean a function. Since it is binary, it should be a function from M times M, Cartesian product, to M. And everything should be interpreted, and such an object is called an L structure. And then an L structure M is a model of a theory T, symbolically M models T, if M satisfies all the sentences from the theory T. The theory is a collection of sentences, so all of them should be satisfied. And here there is, of course, a little thing. One should say, what does it mean, satisfy? And this is defined recursively. Formulas are defined, the collection of formulas is defined recursively using conjunction, negation, quantifiers. And then since you have this recursive definition of the collection of all formulas, you can recursively define satisfaction in a model. So first for this basic atomic formulas, and then, for example, if you have quantifier, there exists X. So the formula there exists X such that phi of X is satisfied in M, if and only if there exists X in M such that M satisfies phi of X, and so on. So we have this natural notion. So, for example, if T is a group theory, what is a group theory from this point of view? It is just the set of the well-known three axioms saying the dot is associative. For every X, there exists Y such that X times Y, Y times X is E. Yes, and the fact that E is the neutral element. All of this can be written as easy axioms using our language of group theory. Yes, and saying that our structure in this language satisfies those axioms is exactly saying that M together with this dot and this E is a group. So in this way, it works like that. Formally, I should say the dot with the index M upstairs, because it's an interpretation of the symbol, and E, let's say, with the M, but we never do that in model theory, and abusing notation, we just use the same letters as were used in the language. Okay, so now Gödel's theorem. So let T be a theory. A theory is consistent, i.e. does not prove a contradiction in a syntactic sense. So I'm not going to formalize it, but there is something called first order logic. So what is this? So you have a language, there are certain axioms of first order logic. An example of an axiom is you take a tautology of the propositional logic. You take a tautology, and in place of these sentences P, Q, R, which appears in your tautology, you can substitute any formula of our language. And we say that, that something like that is an axiom of our theory. And there are a few other axioms, easy axioms, and then there are deduction rules or inference rules. These are mostly actually two, modus ponens and generalization rule. So modus ponens means that if your theory proves phi and proves phi implies psi, then it proves psi. So it's a formal deductive system, and saying that the theory is consistent in the syntactic sense, it means that it does not prove a contradiction. So it does not prove alpha and negation of alpha for any formula. So this syntactic sense consistency is equivalent to the existence of a model of a theory, which is pretty amazing. Of course, this part, if the theory is consistent, then it has a model, because from nothing you build a model. I mean, from the language, from the consistency, and in fact, it is built from terms, from things in the language. But this was a great discovery of Gödel. So a theory is consistent if and only if it has a model. And Gödel's completeness theorem is an easy consequence of this. And it says that for any formula phi, T proves phi, again, according to this deductive system that I mentioned, which I did not define formally, if and only if T models phi, where the second thing means that phi holds in every model of T. So a theory implies a formula if and only if this formula holds in every model of T. So this is completeness and soundness actually here, but okay. And compactness theorem, the most important tool in model theory. A theory has a model. A theory may consist of infinitely many formulas or sentences. So it has a model, so a structure in which all these maybe infinitely many sentences are true, if and only if every finite piece of this theory has a model. That's why compactness, because it reminds compactness. There's some finiteness issue appears here. And this is in practice, this is the most important tool in model theory, this compactness theorem. And now, so it's a non-trivial theorem, yes, Gödel's theorem. Yes.
So in this second bullet, the non-trivial part of the implication is from the right to left, yes, and in the first, the non-trivial is from the left to right.
From the left to right. In the first is from the left to right, and in the second, it is also from left to right.
Left to right is non-trivial,
because,
yes?
Yes, sorry. No, sorry. From right to left, from right to left, yes. So if you know that it holds in every model, you have to show that it can be proved, yes, so yeah.
This is difficult.
Yes.
Okay, thank you.
Okay, thank you for the question. And then for any L structure M, what is the theory of this structure? Okay, structure and model, these are like equivalent terms. But if I don't talk about theory, I usually say structure. When I have a theory, I'm saying a model of the structure. But even about an abstract structure, I can say a model. A model of what? Of its own theory. So what is the theory of the model? So the theory of the model is the collection of all sentences. Sorry, no, something happened. Yes. So this is the collection of all sentences in L, which are true in M, which hold in M. And now a consistent theory is said to be complete if for every sentence phi, we have that T proves phi or T proves negation of phi. Okay? It is not true, for example, group theory is not complete. Because, for example, you can consider the sentence saying every element is of order 2. Every non-trivial, non-neutral element is of order 2. So just from the group theory, you cannot prove that neither that this is true nor that the negation, because there are groups which have this property and which are not. So it's not complete. But for example, the theory of algebraically closed fields of characteristic 0, this theory is complete. It's not completely trivial, but it's easy to show. So it completely determines which sentences are hold and which not. Okay, and the theory of every model is clearly complete just from the definition. What's the theory of a model is for every, because because if you look, so M satisfies phi or not, yes, in the meta theory, in set theory, you know, you have this tautology as P or negation of P. So M satisfies phi or not M satisfies phi. And by the definition of satisfaction, this exactly gives you that that the theory of any model is complete. Okay, and now we have a notion of an elementary substructure. So we say that M, you have two L structures, M and N. M is a substructure of N. Sorry, I don't know what happened where Okay, and we say that this substructure is an elementary substructure using this kind of inequality symbol, curly. If for every L formula phi of x1 up to xn and any tuple of elements from M of length n, the formula phi, when I substitute the elements A in place of variables, it holds in M if and only if it holds in N. So this is the notion of an elementary substructure. Some theories have the property that every substructure is always elementary. This property is called model completeness of the theory. And for example, the theory of algebraically closed fields has this property. And okay, Leeuwenheim-Skolem theorem, since I'm a bit running out of time, maybe I'll skip because I will not talk about it, but it essentially says that if you have an infinite model, or if your theory has an infinite model, then it has an infinite model of arbitrary cardinality. This is the point. If the okay, so and now another fundamental notion is definability. I mentioned definable sets. It's something most important in model theory. So a zero definable set in a structure M, what is it? it is the set of realizations of a formula. So you take a formula and you, let's say in n variables, and you take all the tuples of length n such that this formula holds in the model M on this tuple. So yes, so these are just sets which are defined by formulas. So you see that these are not all sets, but some special sets. So these are these nice sets that come from the structure that we are interested in. And we can also allow parameters from M in the formula. So it's like adding new constant to the language, which corresponds to elements of the model. And when you have a formula phi, you allow also constants from the model M. We call them parameters. And then we do not say zero definable, but just definable. And it means that it is defined over parameters which are additionally involved in the formula phi. So for example, if you take a group and you take an element G of this group, then the centralizer of G, which by definition is the collection of all elements of your group which commute with G, which are commutative with G, then this set is definable because it can be written as phi of M for the following formula. Phi of X says that X times G is equal to G times X. So centralizer is an example of a definable set in a group. Okay, and now types. So let T be a complete theory, let N be a natural number, positive, and let X be a tuple of variables. So what is now an N type, let's say denoted by pi of X, is a consistent with respect to T collection of L formulas in free variables.
Excuse me, maybe, shall we make a break? Or you want after types?
After, actually, yes, because we started a little bit late, so
Okay.
maybe I could like continue for 5 minutes,
Okay,
yes, and do the 10-minute break.
Good.
Is it okay?
Yes, it's okay.
Thanks. Okay, so we have so we have this collection of formulas in free variables X bar, and it should be consistent in the sense that if I take any finitely many formulas from this type, then this collection should be consistent, i.e. it has a realization in every model of T, but by completeness of the theory, it is equivalent to saying that it has a realization in some model of T. So students sometimes make a mistake on the first year that they confuse for all and there exists, and here it doesn't matter, both things are equivalent. Okay, so you take a finite collection of formulas, it has a realization in every model if and only if it has a realization in some model. So because of completeness of the theory, and we say that a type is complete if for every formula in these free variables X bar, either this formula belongs to your type or negation of this formula belongs to your type. So it should determine this. And an example is if A is an element of a model of our theory, then the type of this element, let's say computed in the model M, this is the collection of all formulas which are satisfied by the element A inside M. So the type of A is just the collection of all properties of A which are expressed in our language. So all formulas that are true. So this is an example of a complete type. It's easy to see. And the formulas are, let's say, can be said to be equivalent if the theory, if in every model or syntactically or semantically, let's say in every model, those formulas are equivalent. So in every model, phi of some A bar holds if and only if psi of A bar holds, they are equivalent. And if P of X is a complete type and two formulas are equivalent in the above sense, then we see that a formula belongs to P if and only if the second formula belongs to P, because otherwise, if this was not true, if we had such phi and psi which contradict this, then it would mean that, let's say, phi belongs to P, but negation of phi belongs to psi. Okay, but then this finite collection of formulas phi of X and negation of psi of X, since it belongs to this type P, it should be realized in some model, but it is not realized in any model because of this equivalence that phi is equivalent to psi. So there is no model in which phi holds at some element, but psi not. So we have this, and and the Lindenbaum-Tarski algebra in n variables over the empty set is the quotient of the collection of all formulas by the above equivalence relation, which I denote, let's say, by tilde. So I mean this equivalence relation written here, that the formulas are equivalent in every model. If I divide the collection of all formulas by this relation, then I get some quotient object, and I can define the Boolean algebra structure there using just conjunction, disjunction, negation. But of course, I have to go to the classes module of the relation, but everything is compatible here by the previous remark, so it makes sense. And the zero of the Boolean algebra is the class of this contradictory formula, and the one is the class of this always true formula. And by the last remark, complete types can be identified with ultra filters in this Lindenbaum algebra. So these, you remember these complete types, this was that always a formula, for every formula it belongs or the negation belongs. So it's like a maximal consistent set of formulas. And this maximality, if you pass to this quotient and to the Boolean algebra, it exactly says that types corresponds to ultra filters in this Boolean algebra. And the very last thing before the break, another way of looking at types, which is the most convenient actually. So take any model of the theory, and then if you take two formulas which are equivalent in the above sense, then for every model we have equality phi of m is equal to psi of m. So they have the same sets of realizations because they are equivalent directly from the definition of equivalence. So therefore, this Boolean algebra can be identified with the Boolean algebra just of zero definable subsets of m to the n. So you look at the model, the Boolean algebra of zero definable subsets. So Boolean algebra with operation which are just union of sets, intersection of sets, and the complement. You take this Boolean algebra, and this Lindenbaum algebra is isomorphic to it. And so the complete types can be seen just as ultra filters in this Boolean algebra. So types equivalent. So there is syntactic way. A type is a consistent collection of formula. Complete types is a maximal consistent collection of formulas. But another way at looking at this is a type is an ultra filter in the Boolean algebra of all definable subset of any given model of our theory. Okay, sorry for slightly.
It's okay. It's okay. We make a break when it's convenient for the speaker. Well, are there any questions, comments? Maybe you can take the mic.
In this Lindenbaum-Tarski algebra, elements are formulas or sets of formulas?
Elements are classes of the equivalence relation tilde. So formally, these are sets of formulas. So you take any formula and you take all the formulas equivalent to it, you get a set, and this set is formally a member of this Lindenbaum algebra.
Okay.
But then you have operations. Yes, you can take disjunction, conjunction, but disjunction, for example, it is defined on formulas. But then you induce the operation on these sets, on equivalence classes, and it is well defined. It does not depend on the choice of a representative of a class. It's easy to see. So that's why it is a well-defined operation. Disjunction induces a well-defined operation on equivalence classes.
Okay, and then complete types in this last I don't know, definition or.
This is maybe a
complete. So then it's these are sets of these classes.
Again, yes.
Complete types.
Yes, complete types.
The last dots.
Yes, so it's a collection. Yes, so it's an ultra filter. Yes, so if you have an abstract Boolean algebra, there is a notion of a filter and ultra filter. It is closed undertaking the wedge operation, the conjunction, and undertaking elements bigger in the natural order of the Boolean algebra. So it's an ultra filter in the sense of the theory of Boolean algebras, but it's
so now ultra filter is one set of formulas or this class of formulas, or this is
No, an ultra,
set
if
of
you have
set.
a Boolean algebra, here your notion is a Boolean algebra. So the elements of your Boolean algebra are sets, as you said, but now you can forget it. You have just a Boolean algebra. It consists of some elements, which here are sets, but okay. And then an ultrafilter is a collection, a certain collection of elements of this Boolean algebra satisfying some properties which are belong to the definition. But I think that it's easier and less abstract to look at the last dot. Take a model, and then the Boolean algebra that you get is something easier to grab, because this is just a Boolean algebra of subsets, but not all subsets, but only definable ones. So those which are sets of realizations of formulas. Okay, and then you are more familiar with the notion of a filter or ultrafilter.
No,
yes.
the opposite.
No.
No.
Aha. So if you yes, if you have a Boolean algebra, let's say of sets of subsets of some set, then you have a notion of filter. So it means it is closed undertaking intersections. Yes, closed undertaking finite intersection. If you have two sets in your filter, the intersection should also be in the filter.
Okay, but
and
no,
superset, and then the ultrafilter is a maximal such filter. Yes.
so I'm still a bit lost, because it
Okay.
seems like this ultrafilter is a family of subsets of this Boolean algebra, or
Oh.
is it a single set?
No, and
But-
yes.
Maybe you may.
Okay, but
Yes.
let's call these classes of. Okay, we already
But-
taken the quotient under this equivalence relation. Now let's call this elements, not sets.
Okay.
So then the ultrafilter is a set or family.
It's a
Okay.
set. It's a set. Yes.
Okay.
So that's why the second dot, it may be a bit hard to grab, because the nature of the elements of the Boolean algebra is a bit like, because they are already sets. These element sets. This may
Okay.
confuse. Yes.
Now I get it.
Okay, there's another question. You know, there's a question on the chat. Can you read it and answer?
Given a type, can I just? Yes, of course.
Please.
Yes.
Please, go
The
ahead.
answer is yes.
Yes.
So given a type, can I just omit a formula and get another type? Not maximal. Yes. You can start from a maximal type, or in other words, complete, or from any other, remove any collection of formulas from it, and you get a type.
Okay, are there other questions? Maybe people on Zoom? Okay, if not, let's make a break. I think something like a little bit more than 10 minutes. So we will reconvene at 10 past 10. Okay.
Maybe I should switch off the microphone. Thank you very much again. Okay, so let's continue. We have these types, which are maximal consistent sets of formulas, and complete types can be thought of as ultrafilters in the Boolean algebra of all definable sets in a given number n of variables. And now this way of looking at the space allows us to introduce a topology and treat the type spaces as topological spaces. So the set of all complete types in n variables is usually over the empty set without parameters. It's usually denoted by Sn of empty set. Okay, this is the space of the set of all types. And if we view it as a set of ultrafilters as above, then it can be equipped with the so-called stone topology. I will maybe not recall, because some people maybe are not familiar with Boolean algebras, what is the stone topology. I will say explicitly what this topology is if we look at the types in a syntactic way as collection of formulas. So this is a topology. As you know, a topology can be always given by specifying a basis of the topology, a basis of open sets. So here a basis of open sets consists of all the sets of the following form. You take any formula phi of x, and you take the collection of all complete types which contain this formula. So these are types containing a given formula. So this is a an open set, and it's easy to see that this forms a basis for a topology. And one can see that these sets are not only open, but also clopen. So they are open and closed, because the complement of such a set will be given, we will be such a set for the formula negation of phi of x instead of phi of x. Okay, negation. The complement of the set is the brackets of the negation of phi of x. And and in fact, one can prove that this is a compact, totally disconnected, which means possessing a basis of for the topology consisting of clopen sets, totally disconnected space, which actually plays a key role in model theory. And it is also very important to look at types not over the empty set, but over parameters. And formally, one do it like that. You take any model of the theory, of our complete theory, you take any set of parameters, and a subset of M, and we add new constants to the language, to our language L, corresponding to all elements of this subset. So you can, for simplicity, think you add elements of A to the language, and then you denote the extended language or expanded language by L of A. So it is expanded by the constants from A. And then you consider the theory T of A, which is just the theory of the structure M in the old language, but we look at it in the new language together with all elements of A. Okay, all these parameters from A. So in the formulas, we allow parameters from A. And this is a complete theory again, extending the complete theory T, but now it is in the language L of A, in the richer language. And then we can talk about types over A and the space Sn of A instead of Sn of empty set with respect to T, which formally means that we talk about types over the empty set or the type space Sn of the empty set, but in the sense of the expanded theory T of A. Okay, so this is the usual trick. So we can use, roughly speaking, we can use parameters in our formulas. Okay, and now in a moment I will give an example, but before that, let me discuss one more general thing, namely realizing type and saturation. So let M be a model of T and let A be a subset of M. You remember this compactness theorem that I mentioned, that a theory is consistent if and only, let's say a theory has a model if and only if every finite piece of this theory, finite collection of sentences has a model. So using this compactness theorem, one can easily see directly that each type, complete type, let's say over parameters A from our model M, every type is realized, has a realization, so has an element, it is written here, is realized in some elementary extension of the model M. So you can find, maybe not in M, every finite collection of formulas in P will be realized in M. But if you take all the formulas in P, which is possibly an infinite collection of formulas, then there is no reason for it to be realized by some element in M. But the fact tells us that it will be realized in a bigger model, in a bigger elementary extension. And by realized, we mean that the type of A over A is P. So in other words, this element little a satisfies all the formulas which are in the type P.
Sorry, may I have a question?
Yes.
Could you give some example how big this N might be?
Okay. So these elementary extensions are always constructed in a non-constructive way. Okay, so it's the existence. So, but how big it is? I mean, it can be okay if, for example, your theory is countable, means the language is countable, and let's say the set A is also countable. Then if you have any model N, any infinite model M like here, then you can find N of the same cardinality as M. You don't have to increase the cardinality, but you have to increase the set. There must be some new element.
Okay, thank you.
I will give an example of a space of types on the next slide, so you will see what is going on. But now, using this fact that every type can be realized in some model, this is the consequence of compactness theorem. Then using this fact and doing a recursive construction, usually by transfinite induction, you can prove the following fact, that if kappa is a cardinal number, for example, aleph 0 or aleph 1 or and so on, then every model can be extended to a kappa saturated model, where kappa, denoted by C, where kappa saturated means that for every subset of this model, which is of cardinality less than kappa, every complete type in any number of variables n over this small set, namely set B of cardinality less than kappa, has a realization in C. So you see that this is something like a better information than in the previous fact, because I'm saying that every type is already realized in this special model. No, I don't have to go to a bigger model, but I have to use sets of size less than kappa for a given. So for a given kappa, I can construct a model which realizes all the types over sets of cardinality less than kappa. So, and this leads to the notion of a monster model of the theory. So one can also construct C with the property from the previous fact and with an additional property which is called strong kappa homogeneity, which means that each partial elementary map between subsets of cardinality less than kappa extends to an automorphism of C. So elementary map means that it preserves all formulas. So if you have a map, it is called elementary if for any tuple of elements and the formula holds on these elements if and only if it holds after applying your map F. And whenever you have such a map between subsets of cardinality less than kappa, then it can be extended to an automorphism of the full model. So if you have this kappa saturation from the fact and strong kappa homogeneity mentioned here, then we say that such a model is a monster model. It is not unique, but you can construct such a model, and for doing most of model theory, instead of working, because model theory generally is about working with all models of a given theory. It's a proper class. Yes, you can, but for many purposes, it is enough to work just with in a given monster model. You can express there everything, and it's a very good notion. So, but from this, what I will need later, you have to only remember what is a saturation. So I will be using actually aleph 0 saturation. So aleph 0 saturation means every type over a finite subset is realized in my model. That's it. This is, and such an object exists by this general fact. And now an example. So let us consider the theory of the real numbers. So the universe, my model is R. And what is the structure? I have one binary operation, which is addition, one binary operation, which is multiplication, and one binary relation, which is just the usual inequality between the real numbers. So my language consists here of two binary function symbols and one binary relational symbols. And the interpretations of these symbols are exactly the usual addition, the usual multiplication, and the usual inequality. And now I will describe the space of one types, S1 over this model. So the set of parameters here will be the whole model R, the real numbers. And now, first of all, this theory has quantifier elimination. This is a theorem of Tarski, which says that every formula is equivalent in this theory, is equivalent to a formula without quantifiers. Okay, this is a Tarski's theorem from the 30s, I think, of the previous century. And now if you think a little bit, what are the formulas without quantifiers in one free variable? So you have this one free variable X, and what you can build from this language? You can use addition, multiplication, inequality. So you can build just, and you know, in the part of this theory is that everything is commutative, addition and multiplication and so on. So what you can build from multiplication and addition, these are just polynomials in one variable over parameters from R. So just polynomials with real coefficients. And then what you can do, you can use the logical symbol of equality. So you can write formulas, one polynomial is equal to another, or you can use this extra symbol that we have in the language, in the structure, inequality. So you can write one polynomial is less than another. And that's it. And then you can take Boolean combinations using negation conjunction of these guys. So what subsets of so what are the sets of realizations of such formulas? Okay, if you have one polynomial equal to another, you can move it and get polynomial equal to 0. So you get a finite set. If you take one polynomial is less or equal than another, you move to the other side and you get a polynomial is less or equal than 0 or greater or equal than 0. And then you get just a union of intervals. So thinking about intervals, that a point is an considering all possible intervals, open, one-sided open, one closed. For example, a point will be also an interval like closed. Then you get from this description that the collection of definable subsets of the real line is just the collection of all possible finite union of intervals, where points are also considered as intervals. And there may be intervals which are infinite on one side, and so on. So these are the definable sets. So in this way, we see that every formula using parameters from R in one variable is equivalent to a finite disjunction of formulas defining intervals, proper or not, closed or open, whatever. So this is the description up to equivalence of all the formulas in one variables. These are formulas defining finite unions of intervals. And then when you look at the types, then you have to only think complete types. So how to describe them? So you have to only consider those formulas which define such unions of intervals. And if you think a little bit what kind of types it can define, this is the collection of all types. So for every real number, you have 3 types, PA minus, PA, and PA plus. And you have also extra 2 types, P minus infinity and P plus infinity, where what these types are. So you have the type PA. So this is the type of A over R. This is a type whose unique realization is A. So this is essentially type which is determined by the formula X is equal to A. It does not have any other realization. So in a sense, it's a very trivial type. It is just determined, isolated, implied, or whatever by just one formula X is equal to A. But that's not all. Using only these inequalities, these intervals, you can also see that if you have a point A, then you can obtain something called a left cut at A. So we can say that, okay, X is greater than B for every B less than A. Okay, so it is greater from everything that is less than A, but it is smaller than A. Okay, and of course, and A and B here are the real numbers. Okay, real numbers. So of course, this type does not have a realization in R. Okay, because there is no number which is greater than everything less than less than A, but smaller than A. But in a bigger model, by our general theorems, you can find an elementary extension in a non-constructive way, such that it has a realization. Okay, so it is really a type. And by this quantifier elimination, by what I discussed above, this completely determines a complete type. Okay, because every formula is equivalent to something given by inequalities, by intervals. So this is a type PA minus. And the same you can do on the right-hand side, PA plus. I'm greater than A, but less than everything that is greater than A. So this is PA plus. And we have also these 2 types, P minus infinity, saying I'm less than every real number. And another P plus infinity, I'm greater than every real number. And again, these are types, and by compactness, they are realized in some bigger model. And by this quantifier elimination, there are no other possibilities. It is a little exercise to see, but it's easy to do. So on the picture, it looks like that. You have the real line, you have the usual points, and every point is tripled. Yes, you have PA minus, PA, and PA plus. And additionally, you have P minus infinity and P plus infinity. So this is a set of all complete types in one variable over R. And now there is a question, what is the topology? So we know what is the basis of this topology. You just have to take any interval, closed or open or one-sided open. It can be even degenerated, namely a point, and take all the types containing this interval treated as a definable set. Yes. So in particular, if you take A jak to, czemu to mi się włączyło? Nie wiem, jak to przesunąć. A, to może przez to się włączy. Yes. Can the elementary extension of R for the type P? Yes, of course, it is a total order always. It's not only can it be, but it is always, because the fact that the order is total, so in other words, it's a linear order, is a part of the theory of the structure, yes, because it's given by the axioms. For every x and y, x is less or equal than y, or y is less or equal than x. It's a formula. So if it is true in our structure R, in the reals, it will be true also in every elementary extension. So the answer is yes, in a very strong form. Okay, and now for this topology. So for example, so having this definition that open sets are given by all possible intervals, closed, open, or whatever, you can see what's the topology. But for example, a property, if you take the set PA, I don't know what. Okay, so when you set the tape, any element A in the reals, then you have a formula x is equal to A, okay, and there is only one type containing this formula. One type, this is namely the type of A over R. So this means that the singleton PA is is open, but it is also, of course, closed because the space is Hausdorff. So singletons PA are closed. Okay, but these are the only Klopen sets. So any type PA minus, PA plus, or the others, they are not Klopen. Because if you take any formula which belongs to the type, let's say PA minus, then it will sort of contain a non-trivial interval on the left-hand side around A, and there will be more types, not only the type PA minus, but many other types given by this interval. So, and with this topology, it's a compact.
Sorry, may I have a question? So what would happen if we wouldn't include the parameters? What would be the collection of all definable sets in this case?
Okay, if we don't, but look, an element 1 is definable in here. Yes, number 1 is definable. It's a neutral element with respect to multiplication. So if you define 1, then you can define 2, 3, 4, and so on. So you can define all the rationals, and then if you have all the rationals, so then you are allowed to use them in the formulas because they are zero definable from the language. And then again, when you look at the types, then you get, then you get like.
Okay, I'm happy with
yes,
this
yes. So
already. So if we include the symbol for addition and multiplication, in particular, it means that we also include 0 and 1 as a neutral elements, yes? Yes, in this case, it is equivalent because 0 and 1 are zero definable in the structure. So you can include them. There are little syntactical differences, but not much. Okay,
yes, so.
okay. But we are not stuck, yes?
Yes.
We are not stuck, we have some.
So if you take the types and you consider the extension with the topology, is this always the Checkstone compactization or whatever the word is?
No. I mean the space Checkstone compactification. I will mention it later. So this is always as the so-called stone topology. You have a space of ultrafilters on a Boolean algebra, and there is a notion of stone topology. This is exactly the one that I defined. This is it. And Checkstone compactification is a special space of this kind, where this is the space of all ultrafilters in the Boolean algebra of all subsets, okay, of all subsets of a given set. So it's a particular case. So to get this model theoretically, you have to take your set X. You have to artificially define the language, namely take all subsets of X, and for every subset of X, take a relational symbol and interpret this relational symbol, interpret it as the set from which it comes. And then every subset of X will be definable, namely by the predicate that we artificially added. And then the space of types, even over the empty set, will be precisely the space of all ultra filters on the Boolean algebra of all subsets of X. And then this is the stone-Czech compactification with the usual topology on that. But model theory is more general, because if you consider other languages, then you get other spaces of this type. Yeah, so this is okay. So Czech stone compactification is a particular space. Yes, it's a particular space. It's the Boolean algebra of all ultra filters on all subsets. And model theory generalizes it to some other maybe Boolean algebras, but this is just the stone topology. Okay, and now one more thing, type definable sets. So I said already that one of the most important objects in model theory are definable sets. Not arbitrary subsets of a model, but only those which are definable by some formula. But there are other, a little bit more general sets that are associated, they are strongly related to the language in which we are working. And one such generalization is are type definable sets. So for a type pi of X, which is a partial type, and a tuple of variables, we will say that this tuple realizes pi if tuple A satisfies all formulas in pi of X. Yes, so this is a realization. A should satisfy all the formulas that are in pi. And then what is a type definable set in let's say we are working in the sufficiently saturated model, monster model. So what does it mean a type? We need a saturation to talk about type definable sets. So a type definable set in C is a set X of the form the collection the collection of all tuples in C, n can be equal to 1 or any natural number, but this n is exactly the length of the sequence of variables X bar. So this is the collection of all A which satisfy our type pi. So the set of all realization for a type pi, which is a type over a small, what does it mean small? Smaller than, cardinality smaller than kappa, where kappa was this degree of saturation of the monster model. So to talk about type definability, we have to use sets of parameters which are smaller than the degree of saturation of our monster model. If we want to talk about more parameters, then we have to take a bigger monster model which is saturated enough. So what's the difference between definable and type definable? So definable is a set of realizations of a formula. So it's also a type, just a single formula is also a type, but very special. And type definable is more general. It's a set of realizations, not of one formula, but possibly of collection of infinitely many formulas. And more precisely, we say that such a set is A type definable, where A is the set of parameters which are used in the formulas in the type pi of X bar. And an easy observation using this strong homogeneity of the monster model, that zero type definable sets are invariant under the group of automorphisms of the monster model. And now the definition important for us. What does it mean that a certain algebraic structure is now definable in a model? For example, a group. What does it mean that a group is definable in a model? The definition tells us that this means that the G as a set is definable in this model. So it's a set of realizations of a formula in this model, but not only that, also the group operation or the group law should be also definable. But we have to remember, if the group lives like in one variable in the model M, then the group operation lives in 3 variables. Because so what does it mean that the group operation is definable? It's a graph, X times Y is equal to Z. So this ternary relation should be definable in our model. So both the group itself and the group operation should be definable. Then we say that the group is definable in a model.
First order logic to define relations or higher?
Yes, in a first order logic. I'm talking today only about first order logic, and model theory is about first order.
So how do you define relations?
what? No, relations is a part of a first order logic. You remember a structure or a language consists of function symbols, relational
No, but
symbols.
I thought that to define a relation, we have a formula where relation is like a free variable in it. Well, that's not what we mean.
Look, for example, you have a group, yes? It's very difficult and too much time. Where, to here? I see. Okay. So, for example, you know, what does it mean that a group is definable? So this group should be a subset of our model, and it should be a definable subset, but also the group operation, which is here, which is, let's say, denoted by dot, okay, should be definable. What does it mean? It means that such a relation R of x, y, z holds if and only if x times y is equal to z, okay? So this is a ternary relation defined in this way. So this should be definable. So this is a relation in three variables, and it should be definable in our language, and that's it. So it should be given by a formula using maybe quantifiers, whatever, using the language of the structure N.
Okay, fair.
Okay.
Fair.
Okay, so a few words about general goals of model theory, because I mentioned something about topological dynamics, now about model theory. So one of the most important goal in model theory is to describe the structure of models of possibly wide classes of theories, and also compute the number of models of a given theory, number of models up to isomorphism, models in a given cardinality. So for example, let's say you have a theory and how many countable models it has, or how many models of cardinality Aleph 1 it has, and so on. So this is like the motivating goal and so on, and there are various results of this kind. One of them is, for example, Voigt's conjecture. It's a good example. Voigt's conjecture from the 60s, I think, it tells us that every theory in a countable language, what is the number of countable models of a theory in a countable language? And the conjecture tells us that either finitely many models, or Aleph 0 models, or continuum models, no other possibilities. And this conjecture is still open, okay, in general, but it was proved in some wide classes of theories. For example, stability theory comes to the picture, and Shelach proves whatever it means, stable or omega stable. These are certain combinatorial, for example, definitions, but every omega stable theory satisfies Voigt's conjecture. For example, this is Shelach's theorem. And then for super stable theories of finite rank, it was proved, and a decisive step in it was done by Neversky in his habilitation in late 80s, for example. So, and then another goal, also very important, is to describe the structure, combinatorial, algebraic, or topological, or other, of definable, or more generally type definable or invariant sets of models of a given theory. Another goal is to look at algebraic structures like groups definable, treated as first order structures, and try to prove some structural algebraic or other results under some general model theoretic assumptions. So for example, if the theory satisfies, I don't know, if the theory is super stable, then every field definable in this theory is algebraically closed. And these are quite fascinating results, because assumptions are model theoretic or combinatorial, but conclusions are purely algebraic or even geometric. So this is the field that I was working in the first part of my career so far. So around my habilitation, for example, was about these issues, but then I switched more to topological dynamics. So, okay. And then apply model theory. So here we take general assumptions and get algebraic structural consequences. And here there is another aspect of algebraic model theory. We do not look generally, but we look at a concrete algebraic structure. For example, the theory of algebraically closed fields, or the theory of separably closed fields, etc. And we are trying to deeply study this concrete theory, describe definable set, describe some other model theoretic properties and so on, and then try to apply this knowledge to get to answer some questions in algebra or geometry, Diophantine geometry, for example. And this was done, for example, by Krzysztof in some spectacular papers where he proved Mordell-Lang conjecture about abelian varieties and Manin-Mumford conjecture about torsion points in abelian varieties. So there are applications to algebraic geometry here. And then in recent years, an important part of model theory is the study of interactions with many other branches of mathematics, not only algebra or algebraic geometry, but combinatorics, topological dynamics, non-Archimedean geometry by considering the model theory of valued fields and so on. Okay, and now why can we look at, or how can we look at model theory via topological dynamics? I said because some type spaces can be naturally treated as flows. So this describes this. So this is a very important slide today from the point of view of this talk. So look at Sn of M. So all complete types over a model M in n variables. And I'm saying that if I take the group of automorphisms of this structure, so of course automorphism is a bijection which preserves all the functions, all the relations, or all the constants. Okay, so I have so this space can be naturally treated as odd M flow. Why? So namely, this action of odd M on Sn of M can be seen, for example, as follows. As I said, types can be treated as ultrafilters in the Boolean algebra of all definable subsets. So it's a collection of definable subsets. So how I translate P by G? I just translate all the definable sets which are in P by G. And GD is also definable because this group operation is a definable thing by definition. The group G is definable in my model. So GD is also definable. And it's easy to see that if P was an ultrafilter, then if I translate, I get also an ultrafilter. So that's it. This is my action. And one can check that it's a continuous action. So it's a flow. And and this is especially important when M is a monster model. From the point of view of further development, M should be taken sufficiently saturated and homogeneous. And another type of flow is, so this is general for arbitrary structures or theories. But here, something that works when I have a definable group G. Sorry, I said something wrong. What I said about this, it concerns the next item here. Here, the fact that the translate of G by an automorphism is again definable is just trivial. D is given by a formula. I use a translate by an automorphism. So I just apply this automorphism to the parameters of this formula. So I get another formula with changed parameters. But here I have another context. G is a definable group in my structure, zero definable, and I consider the space SG of M. This is the space of all complete types over M concentrated on G, which means that concentrated means that the formula defining the group G belongs to my type. Okay, so I don't want to talk about the complement of G. I want my type to be concentrated on the group G. Or equivalently, you can say, you can identify it with the space of all ultrafilters of definable subsets of the group G. Not of the whole model, but just of the group G. Just taking the intersection of, you take any definable set in my type and intersect it with G. You can do this operation and see that it's a bijective. I mean, you can identify a type with this. Okay, and then SG of M is naturally a G flow. Namely, you want to say what is GP, what is my action? So I take the type P and as above, I apply GD, but above here it was applying an automorphism, and here it is just translation by an element of G of the definable group. And by the fact that my group operation is definable, I get that GD is definable, and this is a well-defined action. And I can also look at it in terms of realizations of types. So if I take my type P, I can take its realization A in a bigger model, let's say monster model, I can translate this realization by G, and I can compute the type of this translation. So all the formulas that are true about GA. And one can easily see that this is the same object. So I can define this translation either using realizations or just translating all sets inside my type. This is my action. And again, this is an action by homeomorphisms of the type space, which can be checked. So it's a flow. So here is one type of flows in model theory, here another. And here there is also one more using external types instead of types. So using the so-called externally definable sets, but I will skip it, although this plays even a more important role than the second one, but maybe it's a bit too much. So I will not talk about it. And one more example, and then I will state the theorem, and I guess more or less, yeah. So, so M, let M be again this model. By the way, inequality can be defined easily in this model using the squares and so on. It's not difficult. Yes, X is greater or equal than 0 if and only if X is a square of an element. So it's easy to define the order. So it doesn't matter if I use it or not. It doesn't not matter so much. Okay, and now take the circle, unit circle in the plane R squared. So it is of course definable, the circle, because I can write a formula x squared plus y squared is equal to 1. It's a formula of my language, and the set of realizations of this formula is the circle. So circle is definable, and it's also easy to see that the group operation on the circle is also definable. It's a little exercise to make sure that it is definable using addition and multiplication. Because you can look at this at the complex space and look at the formula when you multiply two complex numbers, what happens with the imaginary and the real part. These are given by addition and multiplication easily, some formulas. And now what is the type space over M of types concentrated on G? So it's a very similar picture, and it can be obtained by very similar consideration to the one on the real line. So for every point A on the circle, you have three types: PA, the left cut, and the right cut. Using, let's say, the circular order, you can fix the rotation, clockwise rotation order, and you have this notion PA, PA minus, and PA plus, where they are described here. And in this particular example, one can compute the generic points. There are generic points, and they consist of all the types PA minus and PA plus. So in this case, it is non-empty. And so by some basic fact that I mentioned of Neversky, generic points is the unique, they form the unique minimal subflow. So all the types which are not, except of those trivial types, of course, the types PA are not generic, because if you take the formula X is equal to A, then it gives you an open set. The singleton PA is an open set, and of course, finitely many translate will not cover the whole circle. But if you take any other PA minus PA plus, then you can easily see that any formula which gives you, in fact, by quantified elimination, some interval, so finitely many translates will cover the whole circle. So that's why these types are generic. And now there is this application. Nice and easy application of topological dynamics, of very basic topological dynamics, namely just using minimal subflows. That's it. So this is discovering results. So let G be a zero definable group in an Aleph zero saturated model M. So again, G is zero definable means that the G as a set is definable without parameters in our model, and the group operation, so this relation, is definable in our model without parameters. And I assume that the model is Aleph zero saturated, which again means that if I take any complete type over a finite subset of parameters from M, then it has a realization in M. So whenever I take such a situation, and whenever I can cover my group G by countably many type definable sets, zero type definable sets. So it means that these Xn, they may be definable, but it's more general, it works for type definable. So So this is the sets of realizations of types over the empty set. Or we can only assume that these are Borel. I am not going to talk precisely what it means, but it's even more general. Then you can find a finite subset A of G and N such that G is equal to A times Xn times Xn the inverse. So in particular, this means that G is generated by finitely many Xn's in finitely many steps. Why? Because A is finite, so and G is covered by the Xn, so it means that A uses elements from only finitely many, like Xn1, Xn2, and so on. And here we just use some single Xn. So that's why in this formula, in this product here, there are involved only finitely many Xn's. And how many steps do we need? 3 steps. Yes, because A, Xn, Xn the inverse. So products of 3 elements. Okay, so this result. I don't have really time to discuss this proof, but let me only say that the idea of the proof is that we look at the type space, and in this the type space, and in this type space we distinguish any minimal flow, and working in this minimal flow and with realizations of types, we can apply some basic descriptive set theory like Baire category theorem and so on, and get the conclusion. And let me only say at the very end that this result has a purely model theory free version, which is quite typical in these kind of considerations. So this is the very end. So let me read this. So this is almost model theory free version, and the last remark is fully model theory free version. So let G be a group definable in a model M. I don't assume now any saturation, just any model. And let G to C be a map, which we say that it's also definable. I skip the definition, but this map is also a compactification, meaning that it's a function from G to a compact space with dense image. Then if we cover this image by countably many closed sets, then the conclusion tells us that for some finite A and N, for every open neighborhood of Xn, the original group G is equal to such a product. And then the very last remark is that the typical trick that I already mentioned, if I equipped M with the full structure, so I add predicate for every subset, then every subset becomes definable. So in this restatement, I can remove then the word definable, and I get a purely version, like topological version of this result, which does not use any model theory. I take any compactification of the group, I cover it by countably many closed sets, and I'm saying that there is a finite A and such that I have this property. So this is an example where first topological dynamics is applied to model theory to get this theorem, which uses some model theory terminology, and then using some further tricks, we can eliminate to get such a corollary, which is a completely general statement which does not use model theory. Okay, so thank you very much for your attention.
Thank you very much. Let's thank the speaker. We really don't have time for questions. Maybe if there are any questions on Zoom, I mean, online participants. Or I see something on chat. Thank you for the talk. Okay, and there is a question, I think. Well, is there a question? Can the elementary extensions, have you already answered that? What, just.
Yes, I answered.
Okay. So I think let's finish. If anyone of you in the lecture room has any questions, maybe you may discuss later on, because you will be too late with the next talk. Okay.
Dzień dobry, nie zauważyłem pana wcześniej. A może to powinni słyszeć.